I'd like to start by expressing gratitude to AGCI. This is really a very unique opportunity to interact with scientists and others that you would not normally have the opportunity to do so. And already it's raised some really interesting questions in my mind. I would have never known about chronic kidney disease had I not come here, which is really fascinating. Our group, I thought we kind of talked before this session, rearranged our talks a little bit. Myself and Mary and Anna all work on Aedes aegypti transmitted viruses, which we'll get into a little bit. And we thought it'd be good to kind of give kind of the general perspective from a meteorologist and then talk about some of the complex. Mary and Anna will talk a little bit more about some of the complex issues that you get into in looking at vector-borne diseases. Vector-borne diseases, from a weather perspective, based on what I've seen yesterday, we know a lot more about the impacts of weather and climate on vector-borne diseases, or at least many of them. So I think that this can kind of be, some of what we'll present here can show some of the challenges that we've dealt with in looking at vector-borne disease ecology. And also, so we're going to start with a talk here as kind of a case study of how we've gone through, in one example of looking at the impacts of 21st century climate and population changes on human exposure to Aedes aegypti, the vector of dengue, chikungunya, yellow fever, and Zika viruses. This is a little bit larger scale, kind of global scale study. I would say that most of the work we do is more local scale because the relevance to public health at kind of these community scales is greater. But these types of studies are very important for policy. In terms of the problems we've worked on over the year, I was kind of thinking about the categories they break down into, and in terms of influences of weather, and I think there are kind of three broad categories. One of the categories that we address is kind of basic research, trying to gain a basic understanding of the ecology of a disease and how weather influences that in order to inform interventions. And the CKD talks yesterday, I think, are at that phase. One of the growing areas that we receive interest in and that we're active in is the development of early warning systems or surveillance systems for helping public health decision makers. And then the third type of study, and that's what I'm looking at here, is looking at climate change impacts. And that's a little bit longer time scale. I think that it's always important to think about your audience or what you're trying to influence, and these are typically trying to better understand policy and how you can influence that. And the talk that Jay gave yesterday, which talked a little bit about bringing people in medical and health fields into communicating climate science from kind of the health impacts perspective, I think that's really important, a really important concept to think about, and I'm hoping that this study will help spur some ideas about that and also to understand some of the challenges. Okay, so just a little bit of background on Aedes aegypti. It transmits dengue, chikungunya, Zika, and yellow fever viruses. Mary's going to give a much more detailed background on those viruses, so that'll save me some time. I'll just say that dengue has about 400 million infections on average each year, so very important public health burden. And it's the biggest of those three. Zika, of course, has been very much in the news, and its impacts on microcephaly have been particularly concerning. Aedes aegypti is somewhat unique compared to many mosquitoes in that it lives in close association with humans. It's kind of evolved to be a human commensal. It doesn't breed in the typical places that you would think, like marshes, ponds, wetlands areas. It breeds in human-made containers, barrels and buckets and tarps, bottle caps, septic systems, anything like that. Tires, which are shown here, is probably the favored environment of the mosquito if it had its choice. And they've been responsible for the global proliferation of the mosquito into areas that are not suitable. And also, I think it's important to think about the mosquito itself is constantly bombarding areas that are not climatically suitable, so that if and when they do become climatically suitable, you can be guaranteed that the mosquito will make it there. And the adults live in and near homes, which make it a very effective virus transmitter. The females prefer human blood meals. In terms of the weather linkage, there are numerous ways in which weather and climate influence this mosquito. It breaks down to, in general, warmer temperatures up to a certain point and low variability are favorable for faster development and greater survival. They also increase the extrinsic incubation period for viruses, which is the period it takes from when the mosquito gets a virus from a human to when it can actually transmit it. So for example, in dengue virus, the mosquito needs to, based on the temperature, the virus incubation period might be 7 to 14 days. That's an important consideration because in some areas we have the mosquito, but we don't have virus transmission, and that's probably because the mosquito, the climate is just suitable enough for the mosquito to survive, but not for a long enough period. We also need water for immature development in these containers. For the most part, that comes through rainfall, but there are many examples of human-mediated water sources, i.e. people filling containers, bird baths, water storage practices, those types of things in which water can enable this mosquito to survive. So we also see it in arid and semi-arid regions as well, and humidity also plays a role. The global range of Aedes aegypti is just shown here very simply. And the take-home message here is that it lives in these warm and wet regions that we just described that it was well suited to. So the paper I'm going to talk about today was part of a special issue in the journal Climatic Change, looking at the benefits of reduced anthropogenic climate change on a variety of sectors. So this is a different brace than George's brace. And I think, George, your brace was first to your... Yes, yes, it was. So I brought the issue up and they didn't care. So it's under INCAR's Climate and Human Systems project. And what the key thing here is that we're looking at the difference in impacts between two different greenhouse gas emission scenarios. And both Jerry and Marty talked about these today. RCP 8.5, which is kind of the unmitigated scenario, the trajectory that we're basically on. And then RCP 4.5, which is a mitigation scenario. And one of the key things that I think we were hoping for in this collection of papers is to be able to inform that there is some, there's an investment there's a huge investment in reducing greenhouse gases. What are the benefits of that on different sectors of society, including health? My paper was the only vector-borne disease paper in this special issue, but there were about 5 papers looking at impacts of extreme heat and climate change on morbidity, mortality, and human exposure. So some pretty interesting papers in there if you're an extreme heat aficionado. Another interesting thing here, and I think some of you will be very interested in this, is that we looked at the way that the IPCC has set up the scenarios this time around is that they have these 4 greenhouse gas emission scenarios, of which we're looking at 2. And so those are kind of, low-end greenhouse gas emission scenarios would lead to less climate change, and higher, the RCP 8.5, the highest one, would lead to the most climate change. There are also 5 different socioeconomic development pathways that impact things like population growth patterns and magnitude, GDP, and educational attainment, other kind of factors that we often think about when we're trying to quantify risk for transmission of vector-borne diseases or other human health outcomes. And so we looked at a high vulnerability scenario and a low vulnerability scenario, and we looked at how population might change under these scenarios across the globe and how that might differentially impact human exposure to this virus vector mosquito. There are 23 papers and quite a few participants. So a little bit of background on the RCPs. So we have these 2 different greenhouse gas emission scenarios. The higher end one, RCP 8.5, is no mitigation, high emissions. It leads to global average warming. Sorry, this is a terrible scale, but in kelvins, it's about 3 degrees average global warming by 2080. And the RCP 4.5, which is a mitigation scenario. This is, I have 10 minutes, okay. Jerry showed a plot, I think it was Jerry, maybe it was Marty, showed a plot looking at kind of how much warming we'd see under these. And the Paris Agreement is supposed to kind of follow the 2.6, but in reality, we'll probably see, if everything is implemented, is probably something more like an RCP 4.5 scenario. And even that is maybe optimistic, given the warming that's baked in to the system. But anyways, what we're interested in is the benefit in terms of avoided impacts of this lower climate change scenario. And it's important to remember that these are just global average temperature, which is kind of our proxy for the magnitude of climate change. But what we're really talking about is a more energetic climate system, as Jay put it yesterday. And so we used the same set of climate projections that Marty used in his assessment in Central America. We used what's called the CESM Large Ensemble. CESM is a model, a global climate model, one of about 2021, that informed the last IPCC assessment. It's the one that comes out of NCAR, so it's at our institution. They had a 40-member ensemble of RCP 8.5, and they had a smaller one that they followed on with 15-member ensemble of RCP 4.5. So we use these ensembles to kind of get a sense for, in this case, for internal model variability, kind of the chaos in the climate system. The shared socioeconomic pathways that we looked at, we looked at one called SSP3, which is a high vulnerability scenario. It's also called regional rivalry. Shown in black here are just the different shades of gray and black are population density. You don't need, it's not important what the exact numbers are. This is in 2070, and our future period that we're interested in this study is 2060 to 2080, so kind of a 20-year time slice of which this population projection is the centroid of. And then SSP5, the low vulnerability assessment, is also called fossil fuel development, so you have a lot of human development under that. And so what you have here in this high vulnerability scenario, and I'm going to go to the next slide, is much more isolated countries geopolitically. You have much less cooperation between particularly the wealthy countries and developing countries, much less progress towards meeting development goals like reducing birth rates, raising educational attainment. Health infrastructure is much poorer under this. This is kind of the opposite. You have a much more integrated world. You have a lot of population migration from developing countries into developed countries. And you can see that here in this kind of isolated scenario. The blue areas, and I should describe this scale, the reds are the population growth ratio between kind of present day, year 2000, and the future. So these dark reds are where we have a population quadrupling, particularly there. The blue areas are where we actually have a population reduction. So these green circled areas show in kind of wealthier countries, you have a population reduction projected under this high vulnerability scenario, but you have population growth under the low vulnerability, and you have much lower population growth in the tropics in this low vulnerability scenario. So you can already see that from kind of a risk of vector-borne disease transmission or Aedes transmitted viruses, this is going to be a much better scenario for humanity. You don't have high population growth in areas where you have very high virus transmission potential. So we addressed 3 research questions. The first is, can we just map the global range of Aedes aegypti as a function of climate? And that's been done by quite a few others. So that's not a tremendously interesting question from my perspective, but there are a lot of ways you can do it. And I think the approach we took, which was based on an entomologist, Lars Eisen, who's now at CDC, he was interested in, can we do this really simply? There's a lot of complex ways of doing this. We just use some climatic thresholds based on where we find Aedes aegypti now in the present day climate and look at how those might change in the future. And so that was the approach we used. We used a data set called WorldClim as our base data set, which is a 20-kilometer global data set of weather variables. And then we brought in these RCP projections that I talked about earlier, these two climate projections for 2060 to 2080. And we looked at how Aedes aegypti, the range of Aedes aegypti might change in the future. And then finally, how many humans might be exposed to Aedes aegypti in the future. And we applied those two different population projections to look at that. So this is a map of the current range of Aedes aegypti from this methodology where we just have some climatic thresholds. And the reds and the browns are areas where we have year-round suitability for this mosquito. The reds are where we have year-round suitability in high abundance. The browns are where we have year-round suitability, but we might have a little dry period, so we have a dip in abundance in virus transmission potential. The greens are areas where we do not have year-round suitability. We have seasonal suitability, but the eggs can overwinter. It's warm enough for the eggs to overwinter, which is important because that means the next year you don't need to import mosquitoes in through tire trade or any other way. They actually can just get started. They'll hatch once it gets once it becomes suitable. And then the blues are where we kind of have seasonal suitability, and we don't have the eggs can't overwinter, so it's a little bit harder for them there. And coincidentally, what I won't show here is that types 1, 2, and 3 up through green, but not blue, are pretty much where we see dengue transmission on a regular basis these days in the present day climate. So the blues are areas where we don't see as much transmission of dengue. And these are all known locations of Aedes aegypti in areas where we have decent surveillance. I should point out that this is an artifact of surveillance, not because Aedes aegypti isn't present in in large swaths of sub-Saharan Africa. But you can see that in general we can capture where the mosquitoes are, and also compared to other maps that others have developed, we have a pretty good thing. So we're fairly confident that we can capture the present day range of Aedes aegypti. So now let's project Aedes aegypti into 2061 and to 2080. And these maps take just a second to get oriented with. The top is the RCP 4.5 minus the reference period. So we're basically taking, we're subtracting this present day map from our RCP 8.5 projection, and we're getting a difference map here. We do the same thing for RCP 8.5, this higher greenhouse gas emissions scenario. And the pink areas are areas where we go from a less suitable to a more suitable regime. So for example, this light pink, we went from an unsuitable area to a type 4 area. So if you look at the US there, those areas that are kind of in the middle southeast are areas where it previously was not suitable for aegypti, and now it may be under this projected climate scenario. And you can see that in general, the maps are mainly pinks. It's becoming more suitable in areas. There are some green areas in kind of north central South America where we have a strong drying trend. And drier conditions are not as conducive for Aedes aegypti. So it's not all bad news. This is an interesting plot that we're basically taking. We're looking at the avoided impacts of going with the lower the mitigation greenhouse scenario versus the higher end scenario, RCP 4.5 minus 8.5. And the take-home kind of message at glancing at this is that in general, there are benefits. The green areas mean that it's you have less suitability for Aedes aegypti if you go with the mitigation scenario. And again, this area in South America, where it doesn't dry out as much in the in the lower end climate scenario, we have a little bit worse case there. But for the most part, there are benefits to going with RCP 4.5. This is the final slide of this. This is looking at the projected human exposure, number of humans exposed. In the blue, we have the historical amount of humans, number of humans exposed. It's a little bit shy of 4 billion humans are in areas, one of those 4 areas that are suitable for Aedes aegypti. And then the green and reds are RCP 4.5 and 8.5 scenarios. If we didn't change population, if we held population constant at 2000 levels and just changed climate, which allows us to isolate the impact of climate change alone, we'd go from a little under 4 billion to about 68 to 70% of the human population. So an increase of about 300 million here an increase of about 460 million people here. So, you know, you have a pretty substantial increase just due to climate change, and you have about 50% more increase under the higher end scenario versus the lower end. Now, if we bring in the population projections, not surprisingly, you have very large increase in population by that time. But even if you look at a percentage basis, we go from having, for example, under RCP 4.5, we go from having 68% from climate change alone to 77% if we account for population and climate change, and 80% for the RCP 8.5. So this is important because most of this population, this SSP3 scenario, is a high vulnerability scenario. Most of the people are in developing countries. A lot of the growth, if you read the papers on the storyline, a lot of the growth is in urban slums that are highly exposed. So this is a pretty bad scenario. The SSP5 scenario, which was the low vulnerability population growth scenario where we had more growth in developed areas where we have kind of that type 3, type 4 Aedes aegypti suitability, where it's not as suitable for dengue transmission or other virus transmission. We have a little bit lower growth, but we still have pretty substantial growth in the number of humans exposed, even on a percentage of the total population basis. So in conclusion, climate and population change are both important. I think population, it's pretty clear here that population change is very important. Devil is in the details. On a percentage basis, climate change alone would take the human exposure up to around 70%, whereas we get up closer to 80% if we account for both population and climate change. There's a large shift from seasonal to year-round exposure in developing countries, particularly for the more vulnerable SSP3 scenario. So you have a much longer period of the year in which people would be exposed in these very vulnerable areas. And then we do have, if you kind of break down these results, which we did do in the paper, you have a little bit less, more exposure in wealthy countries, more of a climatic impact there. Lots of uncertainty. I'm not going to show those. Setting the stage for the next two speakers, I think, just talking about the relative role of weather and climate, among other risk factors. Current projections that we make of human health impacts are largely assessing changes in climatic suitability rather than increased exposure to vectors or risk for vector-borne disease transmission, because we have limited ability to project changes in these other factors. So this study tried to make a little bit of an attempt to quantify at least some socioeconomic-based projections of population change. Scale is extremely important. As we scale down to public health relevant scales, which are local, the influence of climate in general for vector-borne disease systems is diminished. So I think that's a really important point to make, and I think Mary will and Anna will talk about that a little bit more.
Thank you very much.